So we're now pretty much at the end of our discussion of completable futures and the completable futures framework. Let's take a little time to talk about the pros and cons of completable futures. And we'll start first by talking about the pros, the benefits, and then we'll talk about the cons. To make this discussion more meaningful and more concrete, we're going to compare and contrast the Java completable futures framework way of doing things with the Java parallel streams way of doing things. And so with parallel streams, you typically do everything synchronously, and with completable futures, you do everything asynchronously, but you can still use streams. It's just that for completable futures, they're typically going to be sequential streams, not parallel streams. So what are some of the benefits of the completable futures framework? Well, first and foremost, if you're going to do asynchronous programming, then it helps you to be a lot more linear and coherent in your programming of said asynchronous programming, rather than having the flow of control bop all over the place and be tangled and confused like a big piece of spaghetti. So you'll see how much cleaner it is than if you were to try to use alternatives for asynchronous programming with things like callbacks and so on. But it supports dependent actions that trigger upon the completion of asynchronous operations. So here's sort of a data flow diagram showing how we might do an image crawl type of operation where we're going to count the images in this particular case. And you can see we start out with something up here that will asynchronously get the HTML page. We get back completable futures for that. We then asynchronously count the number of images on one page, asynchronously crawl the links, and then as those asynchronous operations are done, we can combine them. And so it makes it nice and clean and clear, more or less clear, how things are being pulled together. In other words, these asynchronous operations can be forked. This is forking here between task 1, task 2, and task 3. Chained, like this one, then apply async, then apply, and then ultimately joined through, say, then combine, in a way that makes a fair amount of sense. And as I've mentioned a couple times before, it enables asynchronous programs to look like synchronous programs, even though everything's running asynchronously, either in a background thread or perhaps a pool of background threads. In this particular example, we run supply async as the factory method. That starts running the reduce phase in the background, and the then apply and then accept completion stage methods are going to be running in that single background thread. If we wanted, for some reason, to have these computations running in other threads besides the one background thread that was doing the reduction, we could use then apply async, we could use then accept async, and they would run asynchronously. For this example, that would be overkill, of course, because converting a fraction to a mixed string, an improper fraction to a mixed string, or printing it out, that's a pretty straightforward synchronous operation. You could also optimize the performance and scalability. And this is why we might choose to put up with the extra complexity of asynchronous programming when compared to Java parallel streams. Java parallel streams is arguably simpler to program, but for a variety of reasons, it's typically not quite as efficient because there's just more overhead in having the streams abstraction implemented and provided by the framework, whereas completable futures is a lot leaner and meaner and therefore more efficient, more scalable. You could have these asynchronous operations running in parallel in a thread pool, most commonly the common fork join pool, but it doesn't have to be the common fork join pool if you don't want. It could be other fork join pools that are not common. It could be other types of pools, either predefined pools like fixed size pools or cache pools, or some custom pool that you implement yourself if you so desire to want your own pool. So that's kind of a nice feature. By the way, one reason why you might choose to use a non-common fork join pool is if there's some reason you want the threads in that pool to have a different priority than the common fork join pool has out of the box, which you might or might not want, but if you need it and you still want work stealing, you could make your own fork join pool with the work stealing features, but change the priorities of the threads. Another nice thing about completable futures is you very rarely need to have any threading. In fact, you pretty much never need to have explicit threading. And you rarely, if ever, need to have explicit synchronization unless there's some shared mutable state that all the different asynchronous computations have to converge on and update and read in a concurrent way, like some kind of concurrent hash map that you might use to cache images, which is what we're doing in the bowels of our crawler framework that we're using for this class. If you do need to protect shared mutable state, then of course you can use library routines that come out of, or classes or methods that come out of the Java class library, like concurrent hash map or reentrant lock or synchronized blocks or whatnot. So when you sit down and do some benchmarking, you'll discover that completable futures are usually faster than parallel streams. Not always, but almost always. And we didn't really go over this example in detail, but it's up on my website or my YouTube channel if you want to learn more about it. There's an example I have where I do a bake-off between different implementations of doing image transforming and downloading and filtering and storing and so on. And what you find is that the completable futures implementations are faster, sometimes significantly faster than the parallel streams implementations. And of course, they're all faster than the sequential streams implementation, which makes sense because there's only one core being used for the sequential streams version. So there really is a benefit most of the time to do the extra complexity of programming things asynchronously. Of course, as we always say, your mileage may vary, so you need to benchmark stuff. And there's actually a nice benchmarking framework called the Java measurement handler or something like that. I forget what JMH stands for, but it's basically a way of being able to benchmark Java code in a consistent way to make sure you take out sources of non-determinism in your code. Combining sequential streams and completable futures is often a win. We've seen that in examples that we've talked about. I've shown that. You get to use that in assignment 4. Why is that? Streams can guide the overall flow of control, so you can read the code sort of top to bottom, as opposed to have to play compiler and do loops and if statements and all this other gobbledygook. And you can use the completable futures portion in order to get asynchronous operations to run efficiently. So I like that combination. In fact, I like that combination so much that the next topic we're going to talk about after this one bakes those concepts into the abstraction itself. So the reactive streams model, the paradigm we're going to look at next, actually like this so much that they baked it into the API in a more coherent and comprehensive way than using sequential streams and completable futures. As a general rule of thumb, however, combining parallel streams and completable futures is overkill. There's a funny meme here that says, overkill. Why have one when you can have 200? And it's a minivan full of seatbelts. So that probably won't keep you any safer because you can really not wear more than one seatbelt at a time. But this is not recommended to use completable futures and parallel streams. Using sequential streams and completable futures will get you what you need to do. OK, so that's a quick overview of the pluses, the benefits of the Java completable futures framework.